Okay, so ladies, gentlemen, dear friends, colleague, uh, I'm František Gazdoš from Tomáš Baťa University in Zlín, Czech Republic, and this is, in fact, work of one of my PhD students, Miroslav Palka, who couldn't come and is now on his business trip. So that's why I'm presenting, and it's about the making a dynamic model of a real integrating process with variable coefficients. Structure of my speech is as follow. I will start with motivation for this work. Then I will explain how we chosen the model and how we approximate the variation of the parameters of the model, what functions and what methods we used for these purposes, and I will show you some result and how we evaluated this. Okay, something about the process. It's a real industrial process by one big company, and it's related to tire industry and rubber industry. And it looks like this. There is a closed steam chamber with a material that needs to be processed by high temperature and high pressure, and it's controlled by a valve. There is a valve which is driven and controlled by IPC, and depending on the state of the opening and closing this valve, the steam is going into this space, into this closed chamber to process the material. Uh, in fact, this system, this process is nonlinear in nature, and its parameters change with respect to a given operating point. It means the parameters change depending on the state of the valve position, controlling the steam flowing through this pipe into this chamber, and it depends also on the controlled output, which is the inner pressure, which is related to temperature inside the chamber. Our goal was to prepare a relatively simple control relevant model for this process, which could be further used for control design purposes and control tuning purposes, and optimization of the whole process. So when we measured some responses of this system based on the uh, position of the valve, on the position of the opening of the valve, which can range from 0 to 100%. So in this case, there are 10 responses measured on this chamber, ranging from 10% opening the valve until 100% opening the valve. So where the valve is fully open. Uh, when we analyze these responses, we did some approximations. We found that these simple curves can be in a good way approximated by this transfer function. uh, I guess you are familiar with control engineering terms like transfer function. So these curves can be approximated as an integrating system with some gain, with some time delay. The process has time delay from 0 to approximately one second, depending on the operating condition, and with some other parameters like time constant, damping ratio. So The goal was to approximate these curves to optimize these parameters for every single curve to get the variation of these parameters depending on this state of the control valve. Then these obtained points we were trying to approximate by several methods, polynomial and interpolation-based method, to obtain one simulation model with variable coefficients that would describe well this process and that could be easily used for control design and tuning purposes and for the optimization of the whole process. So when we approximated the single curves, we used this simple criterion to assess the quality of approximation. So that's like least squares. There is a difference between the measured and simulated point squared and normed to the time we used for the approximation. So this is the cost function used for every single curve approximation. And we did this for every curve we obtained. And the overall evaluation of the whole model fidelity was the sum of all these single curves approximation cost functions. For these purposes, we used a MATLAB computing software. I guess you are familiar with this software and its tools for optimization and identification. More specifically, we used the function fmincon, which is in fact a nonlinear programming solver and does function minimization, multivariable minimization with constraints. So you can define easily constraints on the parameters so that they have, for example, some so that they are feasible, they have practical meaning. So there are some examples of the approximation where the single curves were approximated by the integrating model. It's second order. So this is the 10% valve opening approximation of the measured data. So not bad. Then we have there 50% valve opening. Uh, Also quite good approximation by the model. Here you can see the time delay, transport delay, about half a second or a little more. And when we have full opening of the valve, it looks like this. As we can see, the fit of the model is quite good. The measured data are followed by the model, by the character of the model. So that's just example of the approximation of the single curves by the model. Then we obtain these uh, variation of the coefficients of the model based on the opening of the valve. For example, the gain of the system varies like this, depending on the state of the valve controlling the steam. Or, for example, the transport delay variation depending on the state of the valve is like this. So the next goal was to approximate these curves by some methods. So we have chosen two approaches. One was simple polynomial approximation. So we used MATLAB function polyfit of nth order which will give the give the best fitting of the data in a least square sense. That's how it is done. The order of the polynomial have been chosen from 1 to 6, and the best fidelity of the model finally was analyzed and achieved by fifth order polynomial approximation, giving the cost function criterion value like this, which is the smallest one. It means that is the best in this case. There are some examples for approximation of the gain for first, second, third order polynomial and four, five, and sixth order polynomial. When the polynomial is of higher order, then it starts more oscillates, and this may not be so good. Higher order polynomials. Next approach we evaluated was interpolation-based approximation, which was based on cubic spline data interpolation using two functions of MATLAB. One was spline and one was p-chip. In fact, they do the same, but in a little bit different way. They connect the points of the data. There is different in the connection and the derivatives that connects these points, and that's why some results are different for these functions. The polynomial approach discussed in last screen gives you a function. In fact, gives you a polynomial continuous functions which you can use for calculation of the output for every given input. In this case, when we use this interpolation-based approximation, it gives you a vector of discrete values. It will not give you a continuous function, but you can choose the resolution and the range of the vector as you like, so it's not a problem. When we compare the results of these two functions, spline and p-chip for interpolation, we found p-chip is more feasible for us, better, because it provided less overshots and less oscillations compared to the spline function. And what's more, spline function sometimes gave not practically good results. For example, negative gain and negative time delay, and needed to be adjusted the results. So comparing these two, the second one function used for interpolation was better. That was the p-chip function, and there are final values of the criterion for evaluation of the model fidelity. There are some examples of approximation of the variation of the coefficients. For example, again, for the gain k, the blue one is the p-chip, and the red dotted is the spline. As you can see, it's more oscillating, and it even goes to negative values, which is in this case not practically feasible. The same for the time delay. Time delay term approximated by spline. Again, more oscillating, more wild, and p-chip more practically usable. If we look at the whole results of approximations we used, and compare together. So there we can see the polynomial approximation from the first to fifth and sixth order. Between this, the fifth order polynomial gave the best results, but even better results compared to polynomial uh, approximation were achieved by the interpolation-based spline and p-chip function, and the last one was with best results. So when we just summarize, the polynomial approximation results in worse overall fidelity, but the benefit is that you get the function, mathematical function continuous, and also it's in a least squares principle. So it can help if you don't have precise data, if you have uh, some uh, measuring errors and so on. So it can help. The benefit of interpolation approach in this case is higher fidelity of the resultant model parameters, and it means of the final model. But you obtain a discrete output, you not obtain a function, but you can choose the resolution and the range of the vector. So this is not such a big problem. Finally, to show some results, when we approximated it this way and compared the measured responses, real measured responses of the system with the model obtained using this methodology of approximation of coefficients, then I've picked up just one graph where the most visible difference was between these two approaches. There were also some less uh, visible differences, but these were the most visible difference which I have picked up. So that's for opening of the valve 30%, and that is the best polynomial approximation of the fifth order. As you can see at the beginning, it looks good, but when the times go further, it diverges. It's not so good. It's not so precise. But when we compare it to the interpolation-based approach using the function p-chip, uh, it follows, in fact, quite smoothly the measured data, and not only in this case for this operating condition, but also for another operating points. So finally, we have just tried one possible approach of creating a relatively simple structure and control relevant model of a real nonlinear integrating process. As a result, we have a linear model, but coefficients of this model depend on the operating point of the system, in this case on the condition of the controlling valve, and the dependence was modeled and approximated by several methods. One was by polynomial approximation in a least square sense, and the second was tested the interpolation based approach by two functions, spline and p-chip from MATLAB, which are using cubic spline data interpolation. And overall, best results were achieved by the interpolation-based approach using the last function p-chip based on interpolation. However, as I explained, each of them has some pros and cons. What it is good for now, these obtained results are useful for the analysis of the process by simulation means, and mainly for the next step, further step, for control system design and fine tuning of the control system based, for example, on the robust or optimal control theory, because now we have a range of the coefficients which is useful for example, robust control design or another optimal approaches. So that was about just briefly about work of my PhD student Miroslav Palka and me regarding this problem. Thank you for your attention.
Thank you very much.